So today we are going to look at hypothesis tests for the population mean, testing with that X bar. And it's going to be very similar to what we just did with the p-hat, in that we have a null and an alternative hypothesis, and then we had two different approaches for how to test that hypothesis. We had the classical and then the p-value. When we were doing the p-hats, we always did the p-value approach because it was just a little bit nicer. So we're going to look at both approaches again with this one and decide which one is probably the best moving forward with that. So just your requirements. We know that when we're talking about X bar, we still have to have a simple random sample, no outliers, and it has to be normally distributed. So when we were talking about the p-hat, we had to verify that n times p times 1 minus p was greater than 10 and all of that. With X bar, you just need to make sure that it's normal. And if it's not normal, then you have to have at least 30. So I'll have to give you one of those two things. Either telling you that it's normal or n would have to be bigger than 30. And everything has to be independent. Then we will find the null and alternative hypothesis. And we still have the same two options. The null will always be equal to, and then you'll have either left, right, or two-tailed test. So less than, greater than, or not equal to for the alternative. The alpha level will be given to you in the problem. You're not going to have to come up with one on your own. And then from there we can do one of two things. The classical approach is when we find our t, which we've done that before. This piece down here, that's just like your standard deviation. Okay, so it's just saying your value minus the mean divided by standard deviation, which is what we've done every time we find a z-score. So that part isn't new. Because we're talking about X bar, our distribution is that t distribution, which is the very back page of the formula sheet. Remember in the last chapter we had, when we were looking at the X bars, we had used the t distribution. So we'll be using that table today. The classical approach does require a little more hand. And this is kind of why when we did it with the p-hat, we decided that classical wasn't the best, just because there was more room for error. We had a little more we had to interpret on our own. It wasn't as straightforward. And that's still going to be true here. We have left-tailed, right-tailed, and two-tailed. Here's the problem. Your table gives you right-tailed. So if it's right-tailed, it's very straightforward. We just find our t-value. To get the left tail, this is symmetric, so it would basically be a negative of whatever value we have in the table. For the two-tailed, we're going to have to think even more. If I said it was like a 10% probability, you have to divide that up over the two tails. So each tail would be 5%. So if I want two-tail, we will have to divide that by 2 first and get it from there. So I will show you an example and kind of talk through that. But in general, because there's so much more interpretation with this, it is not going to be my preferred method. When we do the p-value approach, it's still the same thing. You get your t-value, your x minus the mean over the sigma. Then you get your probability from the table. And then you just compare that to your alpha. We do have an issue if you're looking at this table. We are very limited here. I only give you a few probabilities up at the top, and my degrees of freedom, we're very limited there. It doesn't give us everything. In general, on these, we are going to do them on a calculator because it is going to be much more exact than what we can do from the table. So I will walk through some by hand and show you. On the homework, the first couple are just going to be having you read some things from the table, so practicing that. But when we get into the actual problems on the homework of testing them, I'm going to let you do it on your calculator because it is more exact than this table will allow us to be. Okay, so let's do a problem. Assume the resting metabolic rate of healthy males in complete silence is 5,710 kilojoules per day. Researchers measured the RMR of 45 healthy males who were listening to calm classical music and found the mean to be 5,708.07 with a standard deviation of 992.05. At the alpha equals 0.05 level of significance, is there evidence to conclude that the mean RMR of males listening to calm classical music is different than 5,710? Okay, first thing, for this to work, it either has to be normal or n has to be larger than 30. So check our criteria. Are we good? Yeah. My n is bigger than 30, so we're good. We can do this. So let's start with our null and alternative hypothesis. We are talking about the mean this time, so your variable will be mu, not p. So our mean for the null is always equal to what? Mm-hmm. The alternative. I want to know if it is different. So that would be not equal. So this is a two-tailed test. All right, I know my alpha is 0.05. Regardless of which approach we take, we are going to need our t-value. So we need the mean and standard deviation to get that. The mean for x bar is just the mean of your null hypothesis, so that's your 5710. Your standard deviation, go back to your formula sheet if you've forgotten. It's on here a couple different places. So you can look under the chapter 10 and it gives you the formula for your t. Or if you look back under chapter 8, the first bullet there does tell you the mean and standard deviation, so whichever way, we're doing the same calculations, just a couple different places it's at. So it's your standard deviation, which was 992.05, divided by the square root of n, which is 45. And remember, we do prefer to keep a few decimal places here. We get 147.88608. So then we need our t-value, which is our value, that's the 5708.07, minus the mean, divided by the standard deviation. And I get a t-value of negative 0.013. All right, so I'm going to finish this problem 3 different ways. I'm going to show you the classical approach, I'm going to show you the p-value approach, and I'm going to show you on the calculator. Basically, every way that we could do it. So for classical, okay, if you look back, we've got our t-value. Now we need to look at our table to get the critical value. When you're looking at this table, you have a degrees of freedom. Remember, your degrees of freedom is always n minus 1. So that would be 45 minus 1. So we have 44 degrees of freedom. Here's the first limitation. Do we even have a row of 44 on this table? No. So this is one of the reasons that we'll do most of this on the calculator, because we're not exact. We'll do the closest we can. What's the closest option? 40 would be closer. So we'll go with 40 degrees of freedom on our table. Okay. So then, since we're doing two-tailed, all right, my alpha is 0.05. That means I have 5%, but I need to split it up over two tails. So what probability am I looking at? So because it's a two-tailed test, you have to divide that. So we're looking at 0.025 and 44 degrees of freedom, which the closest we can get is 40. So our t-value is, if you read from the table, 2.021. Okay, but it's two-tailed. That's the t-value up here. What would be the t-value down here? Negative. So we could put plus or minus. And again, that's only because it's two-tailed. If it was a right-tailed test, we would have looked up the 0.05 for your probability, and the number on your table would have been it. If it was left-tailed, you would have used 0.05, but what would you do for your t once you got it? It would be a negative if you wanted that left-tailed. All right, so then we have to compare these. What this tells me, here are my t-values. We know this thing is centered at 0, right? Essentially, if you're in that shaded area, you reject. If you aren't, you fail to reject. So if you look at your t, negative 0.013, would that be in the shaded area here? No. Negative 0.013 would just be up here, right? To be in the shade area, you'd have to be like more negative than this, so negative 2.5, negative 3, those kinds of things. So this would be in my non-shaded area, so what does that tell me? Fail to reject. Now, does that mean the null hypothesis is true? No, it just means I can't prove it's false. Okay, we don't have enough evidence to reject it. All right, so that's the classical. P-value approach. Starts out the same. You have your test statistic. We have to go to our table, but we're looking at this a little bit differently. Because this is two-tailed, we need to add the probability that t is less than negative 0.013 and the probability that t is greater than 0.013. Okay, that's because it's two-tailed, so we need both of those extremes. We're finding the probability of each of those. We're still talking 44 degrees of freedom, so we're looking at the row of 40 on here. The negative 0.013, positive 0.013, that's what we're looking for in the table. Of course, this table doesn't give us negative, so we have to look for the 0.013. We are looking for that number within the table. Now, here's the other limitation. Do we have anything close to that in our table? No. If we're using this table, we just have to give as close as we can, which is 0.681, isn't it? We can't get any closer than that. So if you go up, the probability of that is 0.25. Does everybody see where I'm getting this?
No.
All right. So on this approach, you are trying to find the probability. So what you are given is the p-value. The p-value is the number in the table. So we know we have 44 degrees of freedom. So the closest we can get is 40. So I'm looking at that row on my table. And my t-value was 0.031. So I want the closest to 0.031 that I can get. Unfortunately, that's not very close. The best we can do is 0.681. So the probability of that is 0.25. So that means each of those things would have a probability of 0.25. So we get that the probability is 0.05, or sorry, 0.5. Now, again, is that accurate? No, we were pretty far off. This is the best guess we can get from our table. Remember, in general, we reject if the probability is smaller than alpha. Since my 0.5 is greater than alpha, that means you fail to reject. Okay, so we're seeing some major limitations with this. We have a lot of guesswork here because our table just isn't good enough. So in general, we will do these problems on the calculator. All right. So we want to go to Stat, Tests, and we are going to do number 2, a t-test. So it gives us the option to base this off data. That would be like if you had listed, I just gave you a bunch of numbers and you put them in your L1. Or we want to base ours off stats. So then it asks us some questions. Mu sub 0, that's the mean of the null hypothesis. So my null was 5710. My x bar, that's the mean of my sample, which was 5708.07. S sub x, that is the standard deviation of the sample, which was the 992.05. What was my n? And then we are testing not equal. So if you go to calculate, it gives us the t-value, negative 0.013. Isn't that what we got when we did it by hand for the t? Then it gives us the p. Now, is that probability what I got when I did it by hand? No. Why? It's more accurate. We were pretty far off, and we knew that going into it. So this tells me the probability is 0.9896. So that is most definitely larger than alpha. There is a 98.9% chance that this could happen. So that is not unusual at all. So we would fail to reject.
So do they do that on purpose? So you have to use a calculator?
I chose this example just to show you why calculator is a better option here. Some of the problems will be nicer ones that your table would be more accurate on, but this one is not.
Oh, we would still fail to reject it, right?
Yep, because our probability is bigger than alpha. All right. Questions there? Let's look at another one then. According to the United States Mint, quarters weigh 5.67 grams. A researcher is interested in determining whether the state quarters have a weight that is different from the 5.67 grams. He randomly selects 18 state quarters, weighs them, and gets the following data. At The alpha equals 0.05 level of significance is there evidence to conclude that the weight is different than 5.67. Okay. We do have a slight problem on this. What did I fail to mention in here? If it's normal. Is 18 enough to assume it's normal? No. So let's just say I put it. That was an error on my part. I should have put in there that this was a normal distribution. Otherwise, we couldn't do this at all. Okay. So what is my null hypothesis?
Mean equals 5.67.
Mm-hmm. What is my alternative?
Not my
For this one, do I have my mean and my standard deviation and all that? No. So how could I get that information? Put it in the calculator. All right, so let's go to, you guys remember how to get there? Stat, edit. You want to put this all in your L1. Clear out anything that's there. Okay. We have two options from here. If I were going to go ahead and find my t-value by hand, we would need the mean and standard deviation from this. So how did I get all that stuff? Do you guys remember what we went to? We do not want a frequency list, so your list should be L1. Frequency list, if you have anything there, just clear it out. And so that does give me the mean and standard deviation, which I would use if I wanted to calculate my t by hand. And so we could get that here, or if we're going to ultimately do it on our calculator, we don't even necessarily have to write that part down. We can just do everything on the calculator. So if we go to stat tests, we want a t-test, but this time is my input data or stats? Data. If you wrote down your mean and standard deviation, you could do it based on stats. But since we have that data entered in my L1, we could do it from there as well. So my mu sub 0, that's the mean of the null hypothesis, so that's my 5.67. Your list should say L1. So if it's not, if you hit second number 1, that would change it to L1. Frequency is 1. Our alternative was not equal to. And so then we can just calculate. So a couple different options here. If you're doing this on your homework, I would appreciate if you wrote down a few things, like let's write down our t-value. And let's write down the probability that it gave us, which was 0.01357. What did I say? 0.01357. Okay. So based on that, what's my alpha level? So this, if the null hypothesis is true, this would happen 1.4% of the time. My alpha level was 0.05, so does that tell me reject or fail to reject? Mm-hmm. Since that's smaller than alpha, we reject the null hypothesis. There's evidence to believe that the mean of those state quarters is different. Any questions there? I want to do one more. This last one, we're going to talk about this. It's not, we're talking about practical significance. Sometimes if your sample is really large, you might get that you would reject your null, and there's evidence to conclude that, but it has no practical significance. There's a statistical difference, but in actuality, that difference really doesn't mean much. I'm not going to test you over this. I'm not going to give you a test and say, was this a practical difference or not? But I just wanted to illustrate that in this next example. So in 2003, the average age of a mother at the time of her first childbirth was 25.2. To determine if the average age has increased, a random sample of 1,200 mothers is taken and is found to have a sample mean age of 25.5 with a standard deviation of 4.8. Determine whether the mean age has increased using alpha equals 0.05. So first of all, can I assume this is normal?
Yes.
Yeah. My n is most definitely larger than 30, so we're good. What is my null hypothesis?
X equals 25.2.
And my alternative?
Means greater.
Because I'm checking to see if it has increased, so that's greater than. Okay, let's just do this on the calculator because we know that's the most accurate way anyway. I don't have actual data, so we're going to stat test number 2, a t-test, but this will be based off stats. I don't have the 1,200 random numbers that I got. So the mean of the null was 25.2. My x bar, the mean of my sample, was 25.5. Standard deviation of the sample was 4.8. My n was 1,200. And my alternative, I'm checking greater than this time. My p is 2.165. P is 0.015. So would I reject or fail to reject? Reject, since my probability is smaller than alpha. Reject the null. There is evidence to conclude the mean age has increased. Okay. So statistically, we found a difference. Now let me ask you. In actuality, we are testing a mean age of 25.2 versus a mean age of 25.5. Is there a big difference there?
No.
No, the woman is still 25 years old. So this is an example where it's not really a practical difference. The age is still the same. It's just a couple months later. But statistically, we do have that difference. Questions there? Okay. So I want to give you guys some time to work, but I'm changing my assignment a little bit, so. Okay. Questions 2 and 4 give you a little practice with reading those numbers from the table, but after that, the rest of them are actually hypothesis testing, and I just want you to do it on your calculator. So those are the only ones where you're actually going to read from the table.